ago, I mean 2015. I come from the area of Vibro, of signal processing, data processing, in everything that is vibratory processes. But I was working a long time in earthquake engineering, and I was working also a long time on toolware monitoring. So for manufacturing system, this is how we came to the idea, okay, how all this knowledge on signal processing for vibratory processes can be used in surgeries. Yeah, at the end of the day, surgery is full of interactions. And the interaction, each interaction is a vibration. Yeah, and this is what we try to assess. We try to extract information through the vibration that the interaction does between the tool and the tissue. So let's start. I will try to go fast now. So yeah, so this is the concept that we are working since years already. Imagine that you have an instrument, whatever instrument. Here I show you a needle, but you can think on a laparoscopic tool, you can think on a robotic tool. And when this instrument enter in contact with the tissue, so you have what we call a vibro-acoustic wave that naturally propagates through the instrument. This is a structural audio acoustic emission. Yeah, and what we can do is we can, with sensors that are outside the body, so without any active component that is in the shaft of the instrument, we can acquire this vibration that is very minimal. Yeah, we have to extract this information to decode this information, and we can use this information for many objectives. Yeah, what we know is that this signal is extremely rich on navigation and haptic information, and the idea is how to extract this and how to provide this for a better that we can provide for surgeons or even for robots. Yeah, so this is, you have to think. I am from an old generation. And when I was a child, I was playing with my friends to this communication, yeah, this toy. So you have to think that the string is the tool, yeah. So how the voice is transmitted is a vibroacoustic wave that travels through the string between the two glasses, yeah. So let me show you here a video, so you can see Nazila there. You can see inside, you have ultrasound image here. Inside there is a soft tissue, is a olive without the stone, and this is a biopsy needle where we connect one of our prototypes. And I want that you hear. Can you hear or not what is happening? I think not.
No, you probably have to share the sound as well when you share the screen.
I'm really sorry again. Share sound. Here it is. Share. Yeah. So now we go again. Yeah, we will start again. Yeah. So you see here. Can you hear now? I hope yes. Yeah. So
yes.
Yeah. So you have the needle, the biopsy needle, and now Nancy will start to insert. We ask surgeons. Surgeons, they don't feel in general when they are entering to the olive. So what you hear there are the tiny interactions that are produced by the needle. When the needle breaks the tissue of this olive. So we can amplify, enhance this, and we can transform these interactions in the audible range for the people. Yeah. So the interesting thing is that interactions are inherent to any surgical procedure. And what we do is to acquire, to transform, and map these sometimes human imperceptible interactions into evident information to the user, in this case to the surgeon. So here I'm showing, and we'll go fast here, I will show how this can be used, for example, for needle insertion into soft tissue. When we insert needles, again, we have this biopsy needle, we can see tissue boundaries. Yeah, we can clearly identify tissue boundaries. We can see fascia punctures, for example. And even there are many characteristics of the audio that can be really correlated with force. So there are characteristics of force that we can extract from the audio with an extremely low-cost sensing modality. So here I show you two videos. Yeah, this is how our development of the product looks today. We have this processing system that provides the acoustic feedback. We can connect, for example, via lure lock to a Veres needle. We can connect to a spine needle via an adapter. And this is how it looks like for the Veres needle, for example. This is one of our old prototypes. He's a pediatric surgeon here in Magdeburg, and you will hear when he crosses the two fascias, and you can also see in the signal. Okay. Yeah. Fascia 1, fascia 2, peritoneum. And all of these, when they have completely different characteristics that we can identify, and we can even classify when the surgeon is arriving to the cavity. The same for spine. Yeah. So you can hear all the path until he arrived to the subarachnoidal space. And also the arrival to a cavity, and this is very important. When we arrive to a cavity, the cavity audio even has characteristics that allow us to have a parametrization of this perforation. And because we can have a parametrization of this perforation, we can classify and we can tell to the surgeon exactly the moment that he is reaching the cavity. We have used this technology also for, I put here the sound of vessel perforation. So in fact, when you have a string, when you have a guide wire, we can connect our device at the proximal end of the guide wire. And what we can do is to hear the interaction of the tip of the guide wire. And there is something very interesting, is that even if you have 1 meter in something that is not rigid, you have a still signal. Yeah. And moreover, every type of event, for example, when you have friction of the guide wire tip with the wall, with the vessel wall, or when you have a perforation, the acoustic signature is completely different. And this allows us to classify events that occurs during the path of the guide wire. We have used also this technology for listening to palpations. Here you can see one of our prototypes. Also, this is a palpation probe used in orthopedic. And we are palpating 3 types of tissues, wood, foam, and ultrasound gel. And you will see, first of all, that this is completely wireless, real time. You can see how sensitive it is. You can see the different signature that each tissue leaves. And you can see that we don't react to the external noise. Yeah, this is very interesting. Hello, 1, 2, 3. And then this information that you are looking there is extremely significant. We can use this and we can correlate this information to mechanical properties of the tissue, and this allows us to classify. Why? Because each tissue has a different audio signature. This is a work that we are publishing now, where we palpate different users, 7 users, different tissues, wood, felt, gel, bone, tendon, and liver, and we can show that we can classify even soft tissues with an accuracy that is over 93, 94%. Yeah, this paper should be soon out there. And what happened is that when we connect this palpator, here we have a Franca-Emica robot to the robotic arm. And because the palpation is completely controlled, velocity and everything, so the difference are even more evident. We have also used Surak for connecting to Da Vinci tools, to robotic tools, yeah. And we have explored 3 main scenarios. So for example, pulsation detection for vessel identification, palpation of underneath bone structure, and to see if we can have texture differentiation as in the case of the palpator. Yeah. And these are roughly the results. So imagine that we put the Da Vinci tool in our carotid. So the carotid, when it pulsates, this moves the full system, the full structural system is moved, and we can also gather this information from the proximal end. Yeah, this will be very interesting when you have pulsatile structure underneath and that you cannot see. Also, again, as in the case of the palpator, we see that we have completely different signature of the signal when we palpate, for example, liver, or when we palpate this pork fillet there and different structures. So this is something that we are doing now since not so long. What we do is to connect the Surak sensing module directly to laparoscopic tools, and we can audify directly laparoscopic tools. So what we can see here, for example, I have a signal example where we have different events. When we open the scissor, close scissor, we cut paper, we cut carton, we cut a string. And the signature, again, is completely different. And now what today we are doing, we are extracting features for being able to classify each one of these tasks, palpation tasks and cutting tasks in general. So yes, I think that we don't have so much time, so let me go to the conclusions. So what we propose here is a non-invasive approach to obtain a completely different type of modality that is really valuable for guidance of instruments. Yeah, we use simply an audio sensor attached to the proximal end of this instrument. We can identify puncture, perforation. We can identify whether a tissue is hard, is soft, or is rough, or is smooth. And the most important is we do not change the tool. Yeah, so we are much less complex than other sensor-based solutions. So yeah, so thank you very much, and I think that yeah, we can pass to the next presentation. Thank you very much.